Hello there, and welcome back. In this video, we're going to continue our discussion of linear algebra by introducing a new object known as a matrix. So last time we talked about vectors and some operations with them. In this video, we're going to be focused on the concept of matrices and the operations within them and their relationship to vectors. So let's just review a couple things that we talked about last time in regards to vectors. So if we have a vector u and a vector v, assuming that both of them belong to the same vector space Rm, and let's assume that they have the structure x1, x2 down to xn. Let's assume v has the structure y1, y2 down to ym. Then we define the sum of these two vectors via the vector x1 plus y1, x2 plus y2, all the way down to xn plus ym. Notice that this first vector has n rows, and technically it has one column. This next vector also has n rows and one column, and this last vector also has n rows and one column. So we say that each of these three vectors belong to this space where vectors live, where each of these vectors have n rows. So let's just summarize that with a little statement. So therefore vectors in Rn have n rows and moreover and one column. So one can ask, well, is it possible to have a structure that has a certain amount of rows and a certain amount of columns? The answer is yes, and what do we call those structures? We call those structures matrices. So generally speaking, we say that if x belongs to Rn, then x is a n by 1 matrix. All right. So a matrix is a structure that has a certain amount of rows and a certain amount of columns. Now, I'm not going to exactly talk about what a matrix represents and what it truly is. There's actually so many beautiful things hiding under these algebraic structures of vectors and matrices, but these are going to become more obvious later on when we introduce a couple more topics. So algebraically, what exactly is a matrix? So matrices, the plural of matrix, can have, it's called m rows and n columns. All right? So generally speaking, a matrix A, which is going to be an m by n matrix, is going to have m rows and n columns. So on the first row, we have first row, first column, first row, second column, A13, that's going to be the first row, third column, all the way out to the first row, and how many columns do we have? So it's m rows, n columns, so that's going to be 1m. And then we're going to have A21, A22, A23, all the way down to A2m, and then A31, A32, A33, all the way down to A3n. This is going to continue all the way down to the last row, which is by definition m rows. So AM1, AM2, AM3, all the way down to AMM. So this is what we refer to as a m by n matrix that has m rows and n columns. Let's look at a couple little small examples. So small example 1. Let's assume I have the matrix 3, 2, 4, 1, minus 3, and 2. So what are the dimensions of this matrix? This is going to be a 3 by 2 matrix because it has 3 rows and 2 columns. If I have the matrix 4 minus 3, 5, 7, what are the dimensions of this matrix? This is going to be a 1 by 4 matrix. Sometimes we call this a row vector. So now that we have some basic understanding of how to represent a matrix, let's talk about some operations between them. So the first, similar to vectors, is going to be scalar multiplication. So scalar multiplication. So we're going to be taking some scalar, let's call it k in the set of real numbers, and let's assume we have some matrix that has m rows and n columns, and this is going to be a matrix. So A lives in the world of matrices that have m rows and n columns, I guess you could say. Right? So what does scalar multiplication look like? Well, it's actually going to look similar to scalar multiplication of vectors. So if I have 3 times 1, 2, negative 1, 0, 0, 3, scalar multiplication is defined to be equal to the product of that scalar with all of the entries in that matrix. So that's going to be 3, 6, negative 3, 0, 0, and 9. So what about matrix addition? So matrix addition is going to work similar to vectors. So matrix addition. So keep in mind, let us assume A is an m by n matrix, and let's also take another matrix B, which is also an m by n matrix. So let us assume Aij is a particular element in matrix A, and let's assume Bij is a particular element in matrix B. So the sum of matrices A plus B, so A plus B is to be equal to the new matrix C, which is also going to be an m by m matrix, which is consisting of a bunch of elements, let's call them Cij, where Cij is defined to be equal to the sum of element ij plus bij. So that's how we define matrix addition. So let's look at a numerical example to sort of see what that means if you're not comfortable with the general structure of it. Let's assume we have matrix A, which is 2, minus 3, 5, minus 1, 0, 7, plus another 3 by 2 matrix, negative 1, 5, 2, 6, 5, minus 1. So remember, if the matrices are not of the same dimensions, both of rows and columns, you cannot add them, at least in the general sense. So this is going to be equal to, so it's 2 plus negative 1, that's going to be 1. Negative 3 plus 5, that's going to be 2. And then 7, 5, 5, and 6. So notice that the dimensions of both of these, 3 by 2, 3 by 2, result in another 3 by 2 matrix. So that's how we do scalar multiplication and also vector matrix addition. Now I just want to make one subtle point clear because I have seen a lot of people confuse these. So let's assume I have a little vector, a 2 by 1 vector, and I add to it another vector CD, also a 2 by 1 vector. Remember that when you add matrices, you get another matrix of the same exact size. So a 2 by 1 added to a 2 by 1 should also be a 2 by 1, where that 2 by 1 is the vector whose first element is A plus C, and the next element is going to be B plus D. So again, this is a 2 by 1 matrix. This is not the same thing as A, C, B, D, the 2 by 2 matrix with those particular entries in those locations. So be very, very careful that these two objects are not the same. So the next operation that is very easy, or technically easy to understand, is transpositions. Transpositions. These are going to be very, very handy in several different applications. So let's consider a matrix, A, m rows, n columns, which is of course going to be a set of elements Aij, where I ranges from 1, 2 down to m, and then j is going to range from 1, 2 down to m. And let's just make sure that these last elements are true. So it's m rows, n columns, right? So for example, if it's like 3, 4, 3, 1, 4, 6, and I say, okay, this is going to be a 3 by 2 matrix. So this is going to be a 1, 1. That's going to be a 2, 1. That's going to be a 3, 1. So notice that the first element, I, ranges from 1 to 3, which is the number of rows that we have. And similar for the number of columns that we have, j ranges from 1 to m. So what is the transposition or the transpose of this matrix A, which we will denote by capital T, sort of like an exponent. So the transpose of an m by n matrix is going to be a new matrix B whose dimensions are n by m. So if it's a 5 by 3 matrix and you transpose, you're going to get a 3 by 5. So the number of rows becomes the number of columns, and the number of columns becomes the number of rows. So how do we define this matrix, Bn by m? It's going to be the set of elements Bij, where Bij is equal to Aj. So the rows become the columns, and the columns become the rows. So that's how we define the transpose of A. All right, so let's look at a couple of examples just to make sure we have a working understanding of it. So if I have the matrix 3, 2, 1, 5, negative 2, 7, and I transpose this, so notice that this is going to be a 3 by 2 matrix. My resulting will be a 2 by 3 matrix. So my first row becomes my first column becomes my first row. So 3, 1, negative 2 becomes 3, 1, negative 2, and 2, 5, 7 becomes 2, 5, 7. So that's the transpose of that matrix. Let's look at another example, 3 by 2. So if I have negative 3, 2, 7, so that's the transpose of our normal vector. So keep in mind this is a 3 by 1, so my result should be a 1 by 3. So that's going to be negative 3, 2, 7. And let's look at another example. If I have 5, minus 3, 7, 0, 6, 5, and 0, 0, 10, so this is going to be a 3 by 3 matrix, and let's assume I want to transpose it. So the transpose of a 3 by 3 is also going to be a 3 by 3. So my first column becomes my first row, so that's going to be 5, 0, 0. Then it's going to be negative 3, 6, 0, and then finally 7, 5, 10. So that's how you do transpositions. And of course, let's mention some terminology for this second example because this is going to be extremely common later on. So it's just some basic terminology. So if you have m rows in one column, this is often referred to as a vector or just a column vector. Both of these terms are often used. And if you have another vector, let's call it y, that has one row and n columns, this is usually called a row vector. And it's very easy to see that the transpose of a column vector is a row vector and the transpose of a row vector is a column vector. We're going to be working with column vectors and row vectors a lot later, but at least be familiar with the terminology here. Now the next operation between matrices that we're going to discuss is matrix multiplication, which is sometimes a little bit difficult at first when you're not totally familiar with it. So if you do remember dot products between two vectors, on the surface it wasn't really obvious why we defined the dot products in that particular way, but we looked at an example of how it sort of follows the parallel structure of the distribution law for example, polynomials. So generally speaking, we know that matrices can take any number of rows and any number of columns. So let's assume that we have a matrix A that has m1 rows and n1 columns, and we're going to be interested in multiplying this by another matrix that has m2 rows and n2 columns. So this product is only going to be defined if these two dimensions agree with each other. So this is only defined, so multiplication only defined if the number of columns of matrix A, so that's the number of columns in A, equals the number of rows in B. So this is the only way that you can multiply matrices, at least in the general sense. So when you multiply these two matrices, and let's assume that you can, that is n1 and m2 are equal to each other, you're going to get a new matrix C, and the dimensions of this matrix is going to be equal to m1 by n2. So the number of rows of this resulting matrix, so that's the number of rows of A, and the number of columns of B. Very strange on the surface of why we would define matrix multiplication this way, but eventually you'll see that this is actually a pretty nice way of defining it. Let's start off with something very, very basic. In particular, let's assume we want to multiply a row vector by a column vector. So let's multiply 3 minus 2, 5, times the column vector 4, 3, minus 2. So why can I say that I can multiply these two objects? So notice that this is going to be a 1 by 3 matrix, and this is a 3 by 1. So if you look at the inner dimensions, they match, so that's good. And my resulting matrix is going to be a 1 by 1. So if this is a 1 by 1 matrix, so that's practically sort of a number, right? What would a natural definition be for this product? Well, that's sort of like a dot product, is it not? So we can define a row vector times a column vector to be equal to the dot product of 3 minus 2, 5 with 4, 3, minus 2. If we define it that way, that's just going to be equal to 12 plus minus 6 plus minus 10, and that's just going to be equal to 6 minus 10, which is minus 4, right? And keep in mind, minus 4 is technically sort of a 1 by 1 matrix, which satisfies what we said before. So what exactly is this particular thing? So technically, if we take this as our definition, then we have a nice little corollary. So therefore, if x and y, so if x and y both belong to Rn, then the dot product of these two vectors is actually equal to the transpose of x times y. So the dot product of two vectors in the same exact vector space is equal to the row vector form of x times the standard column vector form of y. So that's pretty interesting as well. Also, we get a couple other interesting properties if we take this as fact. So also, if x belongs to Rn, and we do x transpose x, so using this little corollary, we have that that's the same as x dot product x, and we know that that's equivalent to the norm of x, the quantity squared. So that's another interesting structure that we have. So let's do a quick example of this. So let's assume we take x to be the vector minus 3, 2, and 4. So what would x transpose x be? So x transpose x, as we already know, is x dot product with x, which is the same as the norm of x, the quantity squared. So that's the norm of x, the quantity squared, so that's going to be 9 plus 4 plus 16, which is going to be equal to 29. So that's some interesting connections between transpositions, dot products, norms, multiplications of matrices, and so on. Now, I just want to make a quick point clear, just in case you don't get confused. X transpose y is not necessarily equal to x, y transpose. They are not necessarily the same, and let's just give a quick example to illustrate that. Let's look at 3 minus 2, 5 times 4, 3 minus 2. So that's going to be a 1 by 3 and a 3 by 1, which results in a what type of matrix? It results in a 1 by 1 matrix. Let's look at another example, in particular xy transpose. So x would be 3 minus 2, 5. Y transpose would be 4, 3 minus 2. So this is going to be a 3 by 1. That's going to be a 1 by 3. What is that going to result in a matrix? That is going to result, because the inner dimensions do agree, right? Because we have a 1 and a 1 as the inner dimension, so you can multiply them. But this is going to result in a 3 by 3 matrix. And a 1 by 1 and a 3 by 3 matrix are not equal. Therefore, in general, that is not true. Very, very important. Keep that in mind. So since it results in something other than a 1 by 1 matrix, well, how exactly do you obtain what that matrix actually is equal to. All right, so let's go ahead and go through an example of how we might be able to construct the general product of matrices. And let's just do a quick example. Let's do 3, 2, 5, negative 1, 4, 6, multiplied by 4, 3, minus 2. So can I multiply these matrices? That's the first thing I need to check. So this is going to be a 2 by 3. This is going to be a 3 by 1. So notice my inner dimensions do agree, so that's really good. And that's going to result into a 2 by 1 matrix. All right. So what is that 2 by 1 matrix going to be? So if this were just a row, just one row and one column, I would just do the dot product between that vector and that second vector. But now I have two rows and a vector. So the natural thing that you may think this is going to be equal to, it's going to be the dot product of 3, 2, 5 with 4, 3, minus 2, and the dot product of negative 1, 4, 6 with 4, 3, minus 2. That would be the natural way you would go ahead and define that. So if that is the case, that's going to be equal to 3 times 4, which is going to be 12, 2 times 3, that's going to be 6, 5 times minus 2, that's going to be minus 10. So that's going to be the first element. And then I'm going to have negative 1 times 4, that's minus 4, 4 times 3, that's going to be 12, and then 6 times minus 2, that's going to be minus 12, and that's going to result in the 2 by 1 matrix. 12 minus 10 is 2, plus 6 is 8, 12 minus 12 is 0, plus negative 4 is minus 4, and that is the resulting 2 by 1 matrix. I'll do another example of that in just a moment, but let's just take a moment and sort of summarize how we multiply matrices in the general sense. Right, so the general structure of matrix products. Okay, so the general form of matrix products. So we have, firstly, an m by n matrix, which is going to have a bunch of rows. So we have row 1, row 2, row 3, down to how many rows do we have? So it's m rows, n columns. So each of these row vectors in this matrix has n columns in it. And then we're going to be multiplying this by another matrix, a p by q matrix, which is going to have a bunch of columns in it. So it's going to be C1, C2, C3, down to how many columns does this matrix have? Well, by definition, that's going to be CQ. So this is going to be resulting in a new matrix. Let's call this M. And what are the dimensions of this particular matrix M? Well, keep in mind this is only defined if n is equal to p, and the resulting matrix is going to be an M by Q matrix. So this is going to be a set of numbers where it's going to be, let's call them Mij. So what are these Mij's going to be equal to? So how would I get the very first element? So I would do the dot product of row 1 with column 1. That's going to give me, so M11 is going to be the transpose of row 1 times column 1. And then how will I get the next element? So for the next element, so this is like M11, so M12 is going to be R1 transpose times column 2, and I'm going to do that all the way down to M1, and that's going to be M1 how many columns, so that's going to be Q, and that's going to be equal to R1 transpose times column Q, the dot product of those two things. And now I can continue that for all of the elements in this particular matrix. So you can clearly see a nice little pattern that Mij is equal to Ri transpose dot product with column J. So that's the general form. If you're in a theoretical structure, then if you're in a theoretical linear algebra course, this is going to be very, very useful in terms of proving a lot of things with matrix products. But if you're in a general course, you probably don't need to be aware of this, but this is an interesting thing to keep in mind. So let's just do another example of matrix products, a nice little 2 by 2 by 2 by 2. So let's do 3 by 3, 4 minus 2 minus 1 times 4, 3, 5, 2. So if you have a bunch of square matrices where the number of rows and number of columns are equal to each other, you're always going to get a square matrix, which is pretty nice. So our first element is going to be equal to this times that in terms of dot product. So 3 times 4, that's going to be equal to 12. Negative 2 times 5, that's going to be minus 10. Then I'm going to do that times that. That's going to give me my next element. So 3 times 3 is 9, and negative 2 times 2 is going to be minus 4. Next, we're going to do this times that. So it's 4 times 4, which is 16. And then minus 1 times 5 is going to be minus 5. And then lastly, we're going to do the second row times the second column. So 4 times 3 is going to be equal to 12. And then minus 1 times 2 is going to be minus 2. So that's going to be equal to 2, 5, 11, 10. And that is my resulting 2 by 2 matrix when I multiply these two 2 by 2 matrices. And that's how the multiplication of matrices generally goes. Now let's talk about a couple theorems that are extremely useful for the multiplication of matrices that you may not have seen, but if you have seen, maybe you haven't proven them on your own yet. So the very first theorem that you should be able to prove if you're in a theoretical linear algebra course is the following. So if A is an m by n matrix, and B also is an m by n matrix, then of course you can add and subtract these matrices, right? So that means A plus or minus B is defined. So when you take the transpose of that result, is this the same as doing the transpose of A, which is an n by m matrix, and then plus or minusing that to the transpose of B, which is also another n by n matrix? Will you get the same result? The answer is yes, and that's a fun, nice little proof to sort of familiarize yourself with the proofs of transpositions. Now, the next theorem is extremely important from the theoretical aspect. So let's assume that the product of A and B is defined, so the inner dimensions are equal to each other. So if that is the case, that means the transposition of the product, is this equal to A transpose times B transpose? You can take a moment, pause the video, and think about that if you want, but actually it's not. It's actually equal to the transpose of B times the transpose of A. So that's a pretty interesting thing. Also, a very important note that you must be aware of is that the product AB, assuming it's defined, is not necessarily equal to each other the product of BA. You should be able to easily construct examples where the inner dimensions agree for one but not the other, but even if they do agree for both of them, for example, both A and B are square matrices, the product does not necessarily commute. So that means matrix multiplication is not commutative. And this is a very important theoretical property that you definitely should be aware of. Now let's talk about some special matrices that you're definitely going to encounter in this series and applications of linear algebra. So special types of matrices. All right. So the first is square matrices, and I've talked about them briefly already. So square matrices are going to be very important. So these are matrices of the form A m by n, where m and n are equal to each other. So the number of rows and the number of columns are equal to each other. So the second special type of matrix is a square diagonal matrix. Some people will define diagonal matrices in terms of rectangular matrices where the number of rows and columns do not agree, but usually we start off with diagonal matrices where they are actually all square matrices. So a diagonal matrix is a matrix of the form n by n where Aij is equal to 0 for all I not equal to j. So the diagonal entries of a matrix, in case you're not already haven't noticed, so for example, if we have 3, 0, 0, 0, 5, 0, and 0, 0, negative 7, this entry, that's A11, that entry is A22, and that entry is A33. Notice that the indices of them match, so 1, 1, 2, 2, 3, 3. So if you're familiar with the Kronecker delta function, which you definitely should be by now, notice that practically this sort of connects with the diagonal entries. So all of the elements off the diagonal, for example in that lower little triangle and this lower little triangle, must be 0 in order for this to be a diagonal matrix. Now some people will allow the diagonal entries, either some or all, to be 0, but generally we try to avoid zeros on the diagonal, and later you'll see why that is the case. Alright, so let's talk about a very important corollary that comes and applies to diagonal matrices. Alright, so the next nice little theorem that we're going to take advantage of on occasions. So let's assume A is diagonal with diagonal entries. Let's call them A, JJ. Then, if n is a natural number, 1, 2, 3, 4, 5, 6, 52, something pretty, no fractions or square roots or anything, then A to the power of n has diagonal entries AJJ to the power of n. So now we can start talking about the powers of matrices. Like if A is a matrix, we can talk about A squared, A cubed, A to the fourth, and stuff like that. So let's look at a little example for this. So let's assume A is the matrix, negative 1, 0, 0, 0, 3, 0, 0, 0, minus 2, and let's talk about A cubed. So A cubed, by definition, is A times A times A. You can try this manually. You can do A times A and then A times A and then, or you could do that A and that A first. Remember, it's not commutative, so it should matter the order. I'm not going to go ahead and talk about associativity of matrix multiplication. I'll let you explore that on your own. But you should try and do this A cubed manually without using this theorem. But one can show that this is actually equal to negative 1 cubed, 0, 0, 0, 3 cubed, 0, and 0, 0, minus 2 cubed using this theorem because this is a diagonal matrix. It's 0 everywhere else. So that means this is going to be equal to negative 1, 0, 0, 0, 27, 0, and 0, 0, minus 8. So a nice quick way of doing powers of matrices if that matrix is indeed diagonal. So the next matrix type that we're going to talk about that is extremely special are identity matrices. Identity matrices. So identity matrices are diagonal matrices with diagonal entries all equal to, take a guess, 1. So the 4 by 4, as an example, identity matrix, I'm going to call it I 4 by 4. Some people just call it I4. This is going to be equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So that is the 4 by 4 identity matrix. And there are some very special theorems that are associated to this. For example, I is a square matrix, so you should be able to do powers of it if you want to. The first theorem is I to the power of n is equal to that same identity matrix, and this is true for all n in the natural numbers, not including, well, you can include 0, I guess. The next theorem that you definitely should know, that AI, so the product of any matrix A with I on the left, and IA, these are all equal to A for all matrices that are square. So that's an n by n matrix. So identity matrices, very, very useful. So the next type of matrix that we're definitely going to be exploring later on in a lot of detail are known as triangular matrices. Triangular matrices. So triangular matrices are of this form. So I'm just going to do examples of them and then give the definition. So let's look at 3, 4, 5, 0, minus 3, 2, 0, 0, 10. Notice that if I look at the diagonal and all of the elements above that diagonal, I get a triangle where the lower triangle is filled with zeros. This is referred to as an upper triangular matrix because all of the values in the lower triangle are 0. Similarly, if I have another matrix, let's do 5, 0, 0, 12 minus 7, 0, 10 minus 4, 3. Again, notice if I look at my diagonal and all the values lower than it, with respect to all of the values above that main diagonal, this is referred to as a lower triangular matrix because all of the elements above the diagonal are 0. So if we represent each of these elements, for example, as Aij, for example, that is element A11, that's A12, that's A13, and so on, an upper triangular matrix formally defined is one that satisfies Aij is equal to 0 for all A greater than J. And keep in mind, I is the row number, J is the column number. And you might want to spend some time with that definition just to make sure you understand sort of what that says. And in case you aren't familiar, the upside down A means for all. Similarly, for lower triangular matrices, that is formally defined as a matrix that satisfies Aij is equal to 0 for all A is less than J. And again, I corresponds to the row number and J corresponds to the column number. So those are what we call triangular matrices. A very important thing that needs to be mentioned is that diagonal matrices, diagonal matrices are both lower and upper triangular because we have zeros above and below the diagonal by definition. So that's a very important observation. And another structure that we're going to explore is known as symmetric matrices. There's another similar concept of matrices called Hermitian matrices, but that involves complex number entries and knowledge of conjugates. We'll explore them later when it's necessary, but for now, symmetric matrices are enough. And these are matrices that satisfy A transposed must be equal to A. So a very basic example, if you look at the matrix A, which is 5 minus 4, minus 4, 6, and look at its transpose, they are actually equal to each other. Therefore, this matrix is what we call a symmetric matrix. And you can sort of try and think about some properties that symmetric matrices always have, because these are definitely going to come in handy later as well. So these are some of the fundamentals associated to matrices. Later, we're actually going to explore the beauty and the underlying structure and meaning of matrices once we start to explore, vector spaces, some of the applications, and the relationship just to column vectors and row vectors and so on. So I hope to see you there. Take care.